might have heard about. What's going on is they take a Neumann algebra and they consider all classical subalgebras. And interesting constructions happen. I don't want to go too much into that, but I think it's fair to say that the basic trick there is to recognize that it's a valid object of study to take the class or coset or whatnot of all commutative subalgebras of a given algebra. On this middle level of Hilbert spaces, this is basically what I think maybe 80% of all the talks this week have been about. You can axiomatize categorically when a category is sufficiently much like that of Hilbert spaces, so you can do lots of construction inside here. And then the basis of a Hilbert space can be translated, if you want, into, most people have talked about Frobenius algebras. I'll tell you in the slide that you really want to have H-star algebras because I'm not restricting any dimension here. And, I should mention some names because that was the point of being embarrassing. In the Neumann subalgebra picture, this was originated by Jeremy Butterfield, a picture I shouldn't later picked up by Andreas Göring, who's here, and also by Klaus Spitters, who's here, and myself and Klaas Hansman. This H-star algebra is joint work with me and Samson, and you should be able to read this by now, but let me put this positively by saying that my collaborators are busy and important man. cat precise. This is basically the most important slide. This is the basic definition that makes everything work. If I have such a basis, an operation that copies some basis, and we consider any projection basically, but let's start with any morphism and make an endomorphism out of it by going up and down. I call such a thing copyable if and only if this projection can slide past the copying. Now notice a few things. First of all, it does not require anything about the unit. I don't like units, so it shouldn't go into this definition. And second of all, this definition works for any morphism K, not just morphisms with domain the monoidal unit. So not just points, it works for any morphism. That's important for us because we want to consider all closed subspaces, not just the one-dimensional ones. So for some examples, the zero subobject and the identity subobjects are always copyable. In the category of Hilbert, we saw that a classical structure corresponds precisely to an orthomodular basis, and from previous work we know that a kernel and Dagger kernel always corresponds to a closed subspace. And the kernel is copyable if and only if it's really a subset of the basis. It's the span of the subset of the basis in a sense. In the category of relations, it's not so nice a priori, because we know by a theorem of Complementarity that classical structure is precisely classified by a Boolean group structure, perhaps multiple ones of them union together. And we know that a kernel is precisely a subset. And it turns out that the only copyable kernels are the trivial ones, the 0 and the 1. So that's not so great. But there's something that can be fixed about that. Because if you remember, where is this definition? I defined it here for any morphism K, and then I double K, so to speak. But I could just have done this for any p from x to x, disregarding K, for any projection. So if you do that, the projections in the category of relations are precisely partial equivalence relations we can characterize. And it turns out that all things are copyable in this extended sense, if and only if they play nice with the group structure. So apparently the category of sets and relations just doesn't have enough. It has more projections than it has subsets. That's the point. So perhaps you should think about projections, is all I'm saying. And from all these fairly weak assumptions, we can now start to prove some lemmas. Here's the first one. You can show precisely that Dagger is copyable if and only if there is something in the middle here which makes this diagram commute. So you should think of X as any Hilbert space, K as any closed subspace, and this as the injection. Then saying that this thing is copyable is precisely saying that I can copy this, and there is a corresponding copying structure on the subspace that plays nice with everything. And moreover, this thing in the middle here is always actually a classical structure in H-star algebra for Riemann set. So that shows that we know precisely now when Dagger monoids are copyable, namely precisely when there exists, when their domain carries a classical structure and the morphism itself is at the same time a monoid and comoidal morphism. So it makes sense to define these as to be the morphisms of classical structures. Notice that they're not preserving units here. In the interest of time, let me skip this. And let's move on to what you can do with these copyable things. Because if you remember that, if you look at all kernels of a fixed object, they form an orthomodular lattice. So we were interested now in just the kernels that means that epsilon is the same as epsilon and then pk. K plug means epsilon is the same. This equality basically. So here you use a K plug copyable and use K copyable. But you know by some general abstract concept that this composition is always the same as this. And of course by definition of orthocomplement, this mean is empty. So you just down to the zero. It means any coelement needs to be zero. So that means again you end up with a category of just one object, which is necessarily the zero object, which is boring. So units of that. Now if you're a category theorist, you might formulate this a bit more fancy in the following sense. You can make things into a functor actually. You can take any Dagger, kernel, monoidal category in the sense that I've been talking about here. Is taking kernels is actually a functor to the category of orthomodular lattices and some kind of morphisms that I don't want to mention now. And in fact taking classical structures, it gives you a category here again with the morphisms that I mentioned that play nice with copyability all the time. And that construction is actually a function on a high level again. But that's not where we're at. The point is that the theorem I showed you is just the same as saying that this diagonal should meet. So that's just a fancy way of saying that copyable things form Boolean lattices. Alright, so much for the lower two levels. Let's move up to the upper one. And now I'm going to restrict myself to the category of null spaces. Up to now I've been axiomatizing things. And you might want to do this for the upper level too, but you need some kind of spectral axiom or something. But let's just stay concrete now and work with the upper spaces. So what we did on the lower level was we characterized when sublattices of the orthomodular lattice are Boolean. I want to do the same kind of thing with algebras, and I want to characterize when subalgebras are commutative in a sense. So what you do is you take a big book of functional analysis out of your shelf, and you collect all these results. First of all, you notice that if you start with any Hilbert space and look at all the operators on it that forms a Neumann algebra, and like alpha my markings are in sense of all the Neumann algebras. And you first notice that the projections of this are always an orthomodular lattice. And in fact, because we're talking about Hilbert spaces, these projections are in fact precisely the same as closed subspaces. You notice that it's a Neumann algebra, so it's generated by its projections in this precise sense, double commutants and set of projections. And if you look at a subalgebra, C of A, then of course also the projections of C are a subset of the projections of A. So that means that by the generation property that the projections of C are also a sublattice of the projections of A. And finally, you know that commutative algebras have precisely Boolean algebras for projection lattices. And the conclusion to draw off all these facts is that commutative subalgebras of a Neumann algebra of this type 1, always correspond to Boolean sublattices of the closed subspaces of the Hilbert space on which it's based. So you can go ahead and reformulate this in terms of copyability and classical structures again, because we're in the category of Hilbert spaces where all this is available anyway. So if I denote by curly C of A all the collection of all commutative subalgebras of an algebra of the given type, then you can show that this is always bijective, just as a set, to the following thing. All the subsets of the lattice of closed subspaces, which are not just subsets but happen to be orthocomplemented sublattices, so just sublattices which respect orthocomplementation, which happen to So what you really want to study is not just this Hilbert space, and not just this CFA, but really the whole category and all classical structures on it. Let me finish up with some remarks then. I didn't really go into the whole complementarity definitions, but if you observe now between these three levels, notions of complementarity, which you could define, there is you can make a tentative definition saying now that things are completely complementary in this way, by saying that its members should be not maximally incompatible, but at least incompatible, and they should give all information if you take them all together. Category speak, that means jointly epic. Right. So there's some exciting things in future work. First of all, this curly C of A is typically taken to be just a post set, which is a kind of border kind of category, if you like. And it's not clear at all what kind of morphisms to take, if any. But this might give a hint, because now we translated this curly C of A into collections of classical structures, and there's a definite natural notion of morphisms between these classical structures. So we might want to translate things back up and might get more interesting things there. Secondly, on this three-layer picture, the lower and the upper levels definitely have a logical flavor, but it's missing, or at least hard to formulate in the middle thing. But of course, the middle thing is sandwiched in between. So if you transfer things up and down, you might get very interesting logical type theoretical constructions in the middle here. That's what I definitely want to look into. And what's maybe most exciting is that on the upper level, the weak point is always that it concerns one fixed algebra. And of course, at the end of the day, we're interested in compound systems. We want to have multiple quantum systems running around and interacting. So now we translate this curly A down to the level of Hilbert spaces. And of course, on the level of Hilbert spaces, there is a tensor product. And we know how things work. So it's very interesting to consider how these tensor products will interact, translating back with the curly C effect, of course. The last 2 points, sorry, I didn't really consider dimension. It might be interesting if I add in compactness to the mix. And finally, the moral of the story is we should, at least I want to, and maybe you can join if you like, consider all classical structures. They should form some kind of vibration, maybe. I'm not sure what it is. Well, I know it's not a vibration actually, but a vibration-like structure. Because over at Hilbert space, there's lots of choices of bases, and it's not really clear how the morphisms work in a vibrational picture. But I think this is a definite indication that's a topic worth of study. And let me end it there. Thank you.
Any questions?
So you're Boolean lattices are possible for some of those that don't have any atoms, right? And
Yes.
you still relate that to copyability, that's also related.
Yeah, so one of the main points actually, I didn't make that clear enough, if I go to this definition of copyability, it works for any generalized points, if you want, not just the atoms. So I don't care if there's atoms in the lattice or not. The definition works and it gives me enough information. See what I mean?
Not yet.
I can try to make it clearly.
Something similar, can I see the generalized definition of classical structure?
Yes. So, yeah, that's maybe a topic for.
Because it depends, given that it depends so strongly on points, are you sure that specializing in them is the same thing? Because that was
Want to do the same thing?
do like for being expected.
Yes, I'm very sure of that.
Yeah, you have to make points there to your last function.
But points in rel are subsets.
Yeah.
So there's a lot of those, so to speak.
So the statement is always specialized.
Yeah.
Does the category of these things, is it also a groupoid like the Frobenius category, or does it have more interesting structure?